Good afternoon, everyone. I hope I'm audible. First, I would like to thank Shankha for having this idea of this conference, and Padmanath as well. I think he's not around today. And thanks to Shanmay for agreeing to swap with me. Tomorrow I am not available. Let's get started. It's going to be a very biased take on effective field theories, mostly based on what I am used to working on, but I'll try to keep the lectures as pedagogic as possible. So let's get started. But before that, if you have any concerns, any questions, even after the workshop or during the workshop, school, you can get in touch with me. And if you would like to keep in touch with the latest happenings at the LHC EFT working group, please do subscribe. So this is a clickable link and you'll be able to subscribe. Yeah. So I'm preaching to the choir here, but here is the standard model of particle physics, which I'm sure all of us in the audience are very well aware of. So we have the various sectors, the matter sector, the force carriers, and the Higgs boson. So the QCD part has already been discussed, is being discussed by two of our colleagues, Professor Spen and Shanmay, my friend. So I won't be discussing too much about QCD in this discussion, but maybe later on in one of the lectures, we might be discussing some parts of effective field theory in the QCD regime. So before I get started with effective field theories, I want to motivate you about why it is important to have very, very precise measurements. And by the end of our discussions over the next few days, I will try to impress upon you why effective field theories are a great tool or great tools to understand precision measurements. So this is something that I want to flash right now, but I'll try to connect the dots in the later lectures. So this is something called the signal strength. So this is about the Higgs that was discovered in 2012, and these numbers are called the signal strengths. Just try to focus in the red box. So the Higgs boson is produced and it decays to various modes. So here we have concerned the Higgs decaying to a pair of W bosons, one being on shell and the other being off shell. And here we see that the number that is being projected here is the ratio of the experimental measurement to the standard model expectation. So if the standard model is true, we would be getting this value to be 1 with an error bar. So this blue band essentially shows us the theoretical uncertainties which are present in these measurements. And we see here that more or less for most of these measurements, the numbers are agreeing within statistical uncertainty within 1. So as you can see that some of these values are a bit different from the standard model expectations, the central values. The reason being that right now, so there could be two reasons. One is that maybe it's a sign for new physics. The other is that we probably haven't collected enough data, and more data will tell us whether we are in the right regime or not. So this is a projection of another experiment, the Atlas collaboration, which shows the various production of the Higgs boson. So I'll be discussing some of that in my next lecture, and decaying to various modes. So if you focus on the red box here, you see that a Higgs is being produced in a channel called the weak boson fusion and decays to a Z boson and a photon, and we see that the uncertainty is still large at the end of the run of the LHC. But for the others, the uncertainties are pretty small, so of the order of between 5 to 10%. So before I delve into effective field theory, so this is the last slide on data that I'm going to show now. You can see here that there are many bars here, and each bar actually corresponds to one of these experiments. So this gray one, which is the machine that we are dealing with, the Large Hadron Collider. So here we see that the uncertainty, is it still working or it's not working? It's still on, yeah. So yeah, here we can see that the uncertainties are of the order of 5 to 10% at best. So by the end of the run of the Large Hadron Collider, we can reach a precision between 5 to 10% on the various measurements. However, if future colliders are being built, we can see that there are several proposals, of which there is the International Linear Collider, the CLIC, the FCC. So these are all projections for from the future collider, and it might be possible that we will be able to constrain, or rather bound, these various interactions to percent or even better precision, per mil level of precision. So if we have such experimental precision, it is imperative that we should also have very good theoretical precision. So in these lectures, I'll try to impress upon you why effective field theories are. You have a question?
Yeah, go ahead. So this, what is this KY? This is a Ikawa?
Oh, so this is delta kappa gamma. So this is a triple gauge coupling. So I did not explain all of these. So these are some of the Higgs couplings. So Higgs with 2 Z bosons, Higgs with 2 W bosons, and so on, so on. And these three are the triple gauge couplings. So 2 W and a Z, 2 W and a photon, and so on.
So these have, right, so these error bars, this uncertainty.
Exactly.
They are very large for these three of them.
Right. So these are quite large at the moment. So LHC will be able to constrain them at the order of some 20% or so. But with the experiments, like for example FCC, we'll still be able to bring them down to of the order of like less than 1%.
That is just because the events are rare, so that's why.
Exactly. So they have weaker couplings, and yeah, they will be produced in more copious amounts. Okay.
Hello.
Yeah.
So when you say that uncertainty is 5 to 10%,
yeah,
how much of it is from the theoretical uncertainty? Let's say from the pattern distribution.
So these are experimental uncertainties I'm talking about. So this is an experimental estimate. So just by rescaling, so Monte Carlo simulation, of course, but using experimental cards. So for example, experimental tune cards, so CMS cards, Atlas cards, FCC cards. So these are the tune cards which are being used, so these experiments have not been done yet. So these will be done. So these are basically projections of what these experiments will be able to constrain. Yeah. The theory uncertainties are not taken under consideration here, only the experimental uncertainties, considering what kind of uncertainties we have now. So for example, if we say have B jets, till what accuracy we can say that these are B jets. So there is an uncertainty on that. So that is extrapolated to some future experiments. We say that okay, our machine is going to improve by this factor. So the uncertainty on such tagging efficiencies would improve by this factor. So these are all like, so these will be like once the experiment starts, we will be able to be sure what these numbers actually are, but now these are projections. So both. So there will be huge number of events so be it an electron-positron collider, which will be a much cleaner environment because there will be much less number of jets, or be it an FCC, like a hadron machine, there will be many more events. So there will be a lot, the cross section will increase massively. So we will have a much more yield, better yield than what we have at LHC. Okay, so usually we talk about discovery through a resonance. So the last particle that was discovered, the last elementary particle, dare I say, not particle, there have been many particles which have been discovered since then. So the last elementary particle that was discovered was in 2012, which was the Higgs boson. So it appeared like this. So all the elementary particles that have been discovered, like most of them, like for example the Z boson, the W boson, the top quark, they all have a resonance structure through which they have been discovered. However, since 2012, we have not been able to discover any such new elementary particles, barring the 750 GeV fiasco that we had. We have not been able to discover any real particles. So what if we are not being able to discover the particle because of certain reasons? What if the new physics that we are looking for is lurking somewhat outside the realm of the energy reach that we have now? So this will form the crux of the matter that I'll be going to discuss today and in the next few lectures, is that if our new physics is at a scale which is heavy and beyond the direct reach of the experiment, that the experiments cannot directly see these particles, then their presence would be felt by the deformation this heavy field creates in certain kinematic distributions that we observe. So we observe distributions like some angular separation between two leptons, say for instance. We see some transverse momentum distribution, or we see some heights of distributions, and we try to measure these as accurately as possible through standard model measurements. So there are lots of people in the audience who do these precision measurements for the standard model scenario, such that we know our so-called backgrounds very, very well. However, even after measuring these backgrounds very well, as precisely as possible, if we see deviations in some angular distributions or some heights of distributions or in the tails of the distributions, we would be able to say, okay, there is a difference. So this might be the artifact of some new physics which we are not being able to see directly. So let's now get started with effective field theory. Yeah. So not necessarily. This particle doesn't need to be like the width by its mass doesn't need to be larger than like 10 or 15%. It doesn't need to be a broad resonance, but the assumption that I have not said here is that it's required that these new particles are decoupled from the standard model particles. By decoupling, I mean that this new spectrum of particles which might lie at this higher energy scale do not get their masses from the standard model like mass mechanism. So that means that they are decoupled. If they are not decoupled, then we will not be, so even if we take the scale to infinity, they will still be talking to each other, and we need to do something else. So I'll be probably discussing a part of it as part of the chiral perturbation theory, which is called the Higgs effective field theory, in one of the later lectures.
Just here in this diagram,
Yeah.
there is this red line that joins these two.
Yeah.
The standard model background with that.
Yeah.
And what is the assumption that is going here? It is that the backgrounds are some way related for the new physics as well
So
as
the gray band is the background.
the standard model one.
Standard model background. The black ones are the data, and the red ones are the various possibilities that can ensue from this effective field theory assumption. So it could be like the what we see actually could be either be aligned completely with standard model, be slightly above standard model, or be slightly below standard model. So now, before going into the particle physics case, I wanted to motivate everyone like how effective theories can be built from a classical case. So let's consider a uniformly charged line. So it's basically classical electrodynamics along the x-axis from x equals minus L by 2 to plus L by 2, and it has a linear charge density lambda. So the total charge is Q equals lambda L. So if we try to find the potential at a point on the y-axis with the y much greater than L, so this is the length of the line charge, and we are going to a distance far away from that. So then we can write down the potential in this form: 1 over 4 pi epsilon naught minus L by 2 to L by 2 lambda dx by x squared root of x squared plus y squared. So if we have this y to be much greater than x, we can use binomial expansion to write down this root of 1 by root x plus y squared as 1 over y minus half of x squared over y cube. So now we can see that this expansion will go in powers of L by y, which will, as we see, be analogous to an effective field theory expansion in terms of the energy scale that we are working at by the scale of the new physics. So only the leading term will dominate here. So the leading term in this case is the monopole term. And if we see here the results, we see that the first term is the monopole term, which goes as L by Y, and the second term, which we would have assumed would be the dipole term, actually drops off because of an odd power in X, and the next term that we get is the quadrupole term, which goes as L cube over Y cubed. So it's a classical analogy of EFT where high energy details are actually encoded in this series in E over lambda. So when we are trying to see this charge distribution from far away, we are not being able to pick up the exact differential part of it, but what we are able to see is a broad view of this line charge. That's why, like, it's an effective theory. It's like it needs to be added, the entire series needs to be added in order to have the full theory, but realistically we won't be able to study every single order. So experimentally we'll be stopping at some order. So till what order do we stop? That is the question, and that is something that will be dealt with in effective field theory when I come to it. So what about particle physics then? So as I said before, the story is going to be very, very similar here. So instead of length, we'll be using energy. So energy basically goes as 1 over length. So the smaller the distance, the larger the energy. So if we want to probe a proton at such small scales, we need to probe it with very, very high energies. But if we go to larger distances, then we have smaller energy. So for example, if we are talking about low energy experiments, say for instance we are talking about some flavor physics scenarios, like some bee physics scenarios. So this, if we are just focused in this low energy regime, we do not require the full differential knowledge of the high energy theory, which is when the scale is much, much higher than the energy of the scale that we are concerned with. So for example, if we are talking about bee physics, like which is around 5 GeV, so the masses of the W boson, which is at 80 GeV, the mass of the Z boson, which is at 90 GeV, the Higgs boson and the top quark, these are the 4 heavier particles which are heavier than the bottom quark. They can actually, their presence will not be felt directly by the bottom quark. However, the artifact of they being there will be encoded in some effective operators that we will be writing. So this is something called the low energy effective theory, low energy effective field theory, or the LEFT, where we have these spectrum of standard model particles, we know them very well, and we only want to study this low energy physics which is below the bottom mass, and then we can basically, something that I will be discussing, integrate out these heavy fields and get some operators, effective operators, which carry the information of these fields through their couplings, but the fields themselves do not exist anymore at this low scale. Yes?
In your classical analogy,
Yeah.
The series that you have,
Yeah.
those are the numbers we are observing.
Yeah.
In this analogy, you assumed already a priori there is a UV completion.
Exactly.
And from there you are deriving this thing.
Exactly.
Whether the UV completion exists in this particular
Yeah.
way or not
Yeah.
requires you to actually sum all of them
Right.
and then say.
Absolutely.
So you are invoking a picture
Absolutely.
which we have no way to verify.
Absolutely.
So, it is in that sense you are calling it effective field theory, but in spirit one doesn't have to.
Absolutely. So this I'll be discussing more later on. This is something called, so there are 2 ways to do effective field theory. So for instance, the thing that I just described, that we integrate out the top quark, the Higgs boson, the Z and the W, which we know exists. So if we think that this is our full theory, then we know that this is the full theory that exists, and we integrate them out and we get an effective theory for the bottom quark or masses below that. So, but the case might be something like we do not have any idea about what this UV theory is. So then there is something that we call matching, which I'll be discussing. So people can take their favorite model. So for instance, I can take some model called a 2 Higgs doublet model, a classic model. Someone can take a model called a leptoquark model. So these are different models with different particle content which are sitting above. But we do not know which is the true theory. We have the standard model which we know of very well, like quite well at the moment. So what we do is that we take both these theories, we integrate out the fields from them, and we get certain operators. So from model number 1, I get, say, M1 number of operators, and from model number 2, I get M2 number of operators. But these M1 and M2 may not be an overlapping set of operators. However, so this approach is called a top-down approach, where I know what is there in the top and I integrate out everything and I get something in the bottom. The other, more agnostic approach is called the bottom-up approach, where I say that, okay, Parthoda, I have no idea what new physics is there. What I do is that I write all possible standard model gauge invariant operators in higher mass dimensions and then see what's going on. So that's a model independent approach in which all of these coefficients of these operators are independent of each other. They are not, so because we do not know what these operators correspond to in the new physics, we have to assume that they are independent of each other. Whereas if we take a full UV theory and if we integrate out the heavy fields, the operators that we will get, the coefficients of these operators will not be independent of each other. They will be functions of these new physics models. So,
Cool.
Yeah.
I have a question. You just said the new, like physics at UV will play the role of coupling modifiers at IR, right?
yes,
Yeah. So when we do a scattering experiment,
Yeah.
essentially we are probing the S matrix.
Yeah.
So if the physics at UV modifies the wave function renormalizations of the fields at IR,
Yeah.
so what we can probe is a combination of the modified coupling and the modified wave function renormalization.
absolutely.
So we can't decouple them.
We
right?
cannot decouple them.
Okay.
So that's the thing. So the effective operators, as we will discuss, will come as some C over lambda to the power n, where C is the coupling of the operator, which we will call the Wilson coefficient, and lambda is the scale of new physics. So we will not be able to decouple this C and lambda. So we will only be able to say some story in terms of this C over lambda to the power n. That's about it. If we want to break this, if we want to say anything beyond, then again we have to make some model assumptions. So for example, what is C? Is C weakly coupled? Is C strongly coupled? If we assume C to be something weakly coupled, then we'll have some statement about lambda and so on. So I'll come to that in much more details. So now we talked about these scales. So I talked about a high energy scale, a low energy scale. So this is something called a separation of scales, and the importance of separation of scales is that it lets us study things properly, because we cannot study all scales together. So for example, when we are studying the Higgs boson at a scale of say 125 GeV, we are not studying something at a tera electron volt. So this separation of scales actually helps us in studying it. It's a practical approach. We cannot study the entire spectrum together, and as I'll be discussing in one of the later lectures, the operators that we construct are constructed at a certain scale, and the data that we have are throughout this spectrum of energy scales, be it in some tera electron volts, be it some mega electron volts, and so on. So when we try to take that operator and map it onto these various data at various different scales, can we do it out of the box, or do we need to do something special? So like any other coupling that we have in the standard model or anywhere, these couplings associated with these operators will also not be constant. They will be energy dependent and they will run. So we will need to take into account the RG evolution of all of these operators. So these are some complicated stuff which I'll be discussing either in the next lecture or in the one after. So as an example,
I have one question. So you're saying in the high energy you have one scale. So is it possible there are, let's say, multiple scale?
Yeah, absolutely. So these kinds of studies have been done where there are multiple scales. So and people have introduced scale of lambda 1, lambda 2 and so on. So I'll be discussing it shortly as well. However, if there is like say new physics starts existing from the scale lambda, so there's new physics spectrum here, then something above it, there's another kind of new physics. So either we can break this entire theory into two different kinds of EFTs, or we can club all of these together and say that my cutoff scale is lambda and do with it. And I'm completely, I don't see what's happening inside that blob above lambda. So I'm like that differential information I'm missing completely.
Okay, so you'll consider one effective scale.
Absolutely. Like, but I'll discuss like when we have multiple effective scales, we will be able to match them. So I'll be in the next slide only. I'll be answering your question. So for instance, so Shanmay will be able to tell this in much more details, I guess. So in LHC collisions, these collisions can also be described by an effective theory, so which is called the soft collinear effective theory. So which is an effective theory between the quarks and the gluons. So if Shanmay is covering it, I will not be. If he is not, then I'll allude to it in one of the later lectures. So what is the concept? So effective field theory is a framework that lets us describe low energy physics without needing the entire details of the high energy dynamics. So as I said that effective field theories, I want to give a disclaimer at the very beginning. So effective field theories are not replacements for UV complete models. Ultimately what we want is a UV complete model which describes our universe as much as possible. So effective field theories in the end will only guide us into the kind of new physics that we might be having. And when it finally guides us, we will be able to say, okay, let's probe in this direction. So what is the key principle here? In an effective field theory, we have the low energy scales and the high energy scales. So we only have, in the effective theory, we only will be talking with the low energy degrees of freedom, and the heavy degrees of freedom will be encoded in the higher dimensional operators and their coefficients. So now coming to Taushik's point, so this diagram basically very nicely describes it. So this is my infrared scale of the theory. This is my electroweak scale, our favorite vacuum expectation values, value around 250 GeV, and this is my UV scale, which could be quite high. So we can have one kind of effective field theory where everything above here is integrated out, and we only concern ourselves. So the L SMEFT will be valid from something somewhere around here down to here, and then we can also have another effective field theory from the electroweak scale, and we integrate out everything on top of the heavy physics which we had already integrated out, and this is another effective field theory that we end with. So, and it is possible that we can map on the coefficients of these various effective field theories. So in many systems, as we can see here, there is a clear hierarchy. So the energy is much less than lambda. So where E is the energy scale of interest and lambda is the cutoff of new physics, and this separation will allow us to expand the various physical quantities, the observables, in powers of E by lambda, much like we had done for the classical case, expanding it in terms of Y by L. Yes.
The parameters in the SMEFT will be related to the parameters in the LEFT. Is that
Exactly.
And the SMEFT, I'm guessing, is the higher dimension operator analog of the standard model. Is it standard?
Exactly.
EFT?
Standard model EFT.
And LEFT, what is LEFT?
It's a low energy effective field theory. Yeah.
You integrate out standard model fields to get there.
I integrate out anything heavier than the bottom quark to get that. So as I said, the W, the Z, the Higgs and the top. Oh, Juhi has a question.
So from what I understood, LEFT should have more number of operators than SMEFT because you're integrating out also top Higgs, W and Z.
Not necessarily. LEFT actually has lesser number of operators. So it's not the number of particles only, because we already have, we know the standard model symmetry, right? We know the symmetry SU3C cross SU2L cross U1Y. So if we integrate out the operators, so I'll be showing the counting in one of the next lectures, but LEFT has many fewer operators than SMEFT.
Okay, okay, maybe conversely, what I wanted to know was, since there are many low energy experiments already,
Yeah.
and also we have electroweak scale measurements, so has it already been possible to constrain some portion of LEFT from data?
Yes.
And
So all the flavor physics observables that you see, most of these are done in the LEFT scenario. They are not studied in the SMEFT scenario. There are results for SMEFT, but most of the results are in the LEFT case. So when you hear these operators, this O9, all O10, these are all LEFT operators.
okay, and they would also be valid for SMEFT, but of course the values can run and change.
Yes, they will. The same structure would also exist in SMEFT. Yeah. So this is this famous theorem called the Appelquist-Carrazon theorem, which tells us that if we have heavy fields, sorry, yeah.
I'm probably jumping gun, but when you do this matching, do you the maximum number of dimensions you keep in the SMEFT, the maximum number of dimensions of operators you keep in the SMEFT, should it be equal to the number of maximum number of dimensions you keep in the LEFT as well?
Exactly. So we have to match dimension by dimension. So like the mass dimension should be matching. So otherwise, so the thing is that this also I'll be discussing in more details. So the operators will be suppressed by some mass scale to the power something. So that should match. So the dimensionality of the operators should match.
Let's say in the current energy scale, we don't see any signature.
Sorry, I didn't understand the first part. Yeah.
In the current energy scale of the
Yeah.
LEC, we don't see any signature of the new physics prominently.
Yeah.
So if you construct some EFT in the high energy scale, let's say some UV theory.
Yeah.
So how can I understand this asymptotic behavior that your high energy theory, let's say all sort of operator, is going to die in the current energy scale? And so is that the Wilson coefficient is running is responsible?
Yes. So the Wilson coefficients will be running starting from the energy scale at which it is created, and then it will run down all the way to where your measurements need to be made. So just to give you something like well in advance, the operators won't only run, the operators will mix among themselves. They'll be mixing among operators. There'll be creation of new operators. So if you recall your QFT course, so you have studied the anomalous dimension matrix. So from there you will be able to see how the operators run into each other, they mix, and some new operators are also created.
So in the RG sense,
Yeah.
when we have a theory,
Yeah.
we can add as many number of irrelevant operators we can do.
Yeah.
It helps to get into the fixed point, but the fixed point there, when we do in the RG picture, is known very well.
Yeah.
So we don't want to mess it up.
Yeah.
So if I want to connect this to the RG picture, so how will I do that, or is it possible to do?
So I'll be discussing it in one of the later lectures that I already had in mind, but we cannot just write any number of operators. So we have a lot of operators. I'll be discussing a simple case here, but many of these operators will either be gotten rid of by the equations of motions of the scenario that we have, like the theory that we have, or by integrating by parts. And then we'll only have a certain number of gauge invariant operators which will abide by in this case the gauge symmetry of the model that we have in hand.
But your the Lagrangian is the standard model Lagrangian, and then you're adding.
My Lagrangian will be the dimension 4 standard model Lagrangian plus these deviations.
For this RG running, let's say, so for this top-down approach, for the running unit, you need to know all those Wilson coefficient at certain energy scale.
So we don't know the numerical values of their of these Wilson coefficients. We know how they will change. So we only know we'll only know their energy dependence, and we'll know their constraint from the experiment. But these Wilson coefficients are completely unknown. So if it's from a top-down approach, these Wilson coefficients will be functions of that model's parameter. So for example, say you take a 2 Higgs doublet model. these Wilson coefficients will be functions of the model parameters of the two Higgs doublet model, say the quartic coupling of the second Higgs, the mass of the second Higgs boson, the second Higgs field. These are the things that the coupling will be.
Yeah, even that has to be measured at certain energy scale.
Yeah, so right now we do not have measurements, right? We can only constrain them because we haven't observed these operators per se. Until we observe something, we do not know what their values are. So we only know their theoretical constraints, like from perturbativity or from unitarity, what kind of bounds they have. But beyond that, we don't know anything about them. So they are just parameters for us, and the parameters will run.
So if I know,
You
if I
can go ahead and see all this picture with full glory when the time comes.
Yeah, I'll plans to like
okay,
do all of those.
we can discuss later.
Yeah, so this Appelquist-Karazon theorem basically tells us that the heavy fields contribute corrections of the form delta O, which is the operator, the change in the operator E by lambda to the power n, where n is the number of heavy fields that we have. So for E much less than lambda, the influence of heavy fields is suppressed. So even though I say that it's suppressed, but that doesn't mean that it's negligible or it's not important. So now, yeah.
What's n?
So n is basically the dimension. So at a certain dimension, so for example, if we have dimension 5, n will be 1. If we have dimension 6, n will be 2, and so on.
And why do you call? I'm just trying to understand. How is this a theorem in the sense that I mean, what are the assumptions that go into proving such a thing?
So the most important assumption is decoupling. That the new physics that we have is completely decoupled from the physics, the low energy physics that we are dealing with. That's the assumption that goes into the and also the next assumption is that E is much smaller than lambda, so that we can make the Taylor expansion. So now I have the formal EFT decoupling. So what is decoupling? I'll be illustrating it with a few examples. So when we talk about a UV theory, the full dynamics is given by this Lagrangian LUV, which is a function of the light degrees of freedom or the light fields phi and the heavy fields, which is the H. So phi and H are just two placeholders. They can be multiple number of fields. So there could be multiple light fields, there could be multiple heavy fields. So the low energy focus is that at energies E, which is much less than the scale of the heavy physics, which is also like the scale of heavy physics. I'll be using this nomenclature interchangeably. MH could sometimes be written as lambda. So the heavy field mass is basically the new scale lambda that we are dealing with. So the experiments will only be dealing with the phi external states, which is the light external states. So when we are at an energy regime here, we will only be dealing with all our cross sections that we will be dealing with will involve only the fields phi and not the fields H. So the effects of H will only be encoded in effective parameters. I will be coming to this step by step, so that's why I wanted to build this story. So let's take an example of QED, light by light scattering. So this is the diagram for light by light scattering. So the photons, they scatter via virtual electrons. So if we have very low energy photons which are below the E plus E minus threshold, then we cannot see the structure of the E plus E minus. So the on shell electrons don't appear, and we see it as an effective interaction. We don't see what's going on in here. Like this is basically just a Feynman diagram. We do not see we cannot, in a very naive way, we cannot make a resolution of the E plus E minus inside this photon light by light scattering. Exactly. So yeah, the next one is basically Fermi theory. So when we have the muon decay, it proceeds via virtual W boson. So and since the mass of the muon is much smaller than the mass of the W boson, the details of the full standard model are not just required. We can just trade it off with an effective vertex, and we can write the theory. So let's have an introduction to integrating out heavy fields. So because we'll be using this quite a lot, and I wanted to start with very simple cases. Yes, please.
Yeah, last slide, its mass of the muon is very less than mass of the W, or the momentum flow is much less than MW.
Momentum flow, like here we are talking about mass scales, the energy scales. So
When you-
it's a muon being decay. It's a muon which is decaying. It's not necessarily a muon which is produced at very high energies. It could just be a muon at a fairly like. So I don't understand the question. So it's the mass scale that we are talking about.
So when you write the propagator, you have this P square minus MW square, and then you
Yes.
expand
Yeah.
P by MW
Exactly.
square.
So, okay, I'll be discussing this as well. So, basically, this is what you can write. Q squared less than equal to mu squared much less than mw squared. The momentum flowing. Okay. So let's take a full theory which is described by this Lagrangian that I showed in the last slide. LUV as like phi and h are the two fields which are the degrees of freedom. So if we take a path integral framework, the complete dynamics is basically written down in terms of a partition function which is the ZUV. So we have these various, so these are basically the integrals over all possible fields like d phi and dh, and then we have the action here. So we have the Lagrangian, the full Lagrangian LUV phi h, and then we have these external terms which basically give rise to the correlations between the various fields. So the effective theory is basically at low energies when E is much smaller than mh. So mh is the mass of this heavy field h. The experiments only probe this field, this light field phi. So one can basically, what one can do is that they can just set jh is equal to 0, and they can say that okay, this is my effective partition function ZEFT Zj of phi is equal to ZUV j of 0. But do you think this is realistic? This is not realistic because there is a lot of information in this action which if I just put the external source to be 0, it's missing out. So it's not a very good statement that we just take out a heavy field. That's not our intention. The heavy field exists. We cannot just put the external source to 0.
But the H path integral is still non-trivial.
Exactly. So this is a non-trivial thing.
Yeah,
So
JH can be set to 0, but you
but
still
this is not still 0. Exactly. Yeah. So this is not a realistic scenario, but because this doesn't describe an effective theory. What we can do instead is that we can have a ZEFT J phi, which is an integral over this light fields, and then the action instead of the LUV phi comma h plus J phi phi plus JHH, we have an LEFT phi plus J phi of phi.
That equation that you're defining as ZEFT this way,
Yeah.
then that equation has to be that makes sense, right?
It still doesn't make sense because if I set JH equal to 0, this LUV phi h suddenly doesn't magically become the LEFT phi.
It doesn't, but isn't this what you meant by matching or no?
No, this is not what I meant by matching.
Okay.
Matching is what I meant by like there are two different EFTs, so or one UV theory and one EFT, and we integrate out the heavy fields. In here, I have not integrated out the heavy fields.
Aren't you doing that by doing the path integral over the heavy fields?
No, but I will be doing the path integral over the heavy fields, but then this is still not that. This ZEFT, like this non-trivial interactions between the phi and the h still exists in this version of the ZEFT.
No, I'm not treating this as a definition of the ZEFT. The ZEFT, in what you give in the next slide, is
Yeah.
the definition of the ZEFT, let's say.
Yes, yeah.
Then, given this, the path integral done this way
Yeah.
should agree with the path integral done with the UV theory, right?
Absolutely.
Yeah, that's what I was saying.
Barring some order m to the power minus 2, m to the power minus 4 terms. So
Sure,
this is
but
the difference that we need to quantify.
Sure, but ZEFT defined this way if that was a definition sign instead of an equality.
Absolutely,
The other equality.
absolutely, absolutely.
Yeah, but then in this previous path integral, there is no path integration over JH. It's an external source.
Exactly.
So you have to set that to 0 and do the H path integral to get that.
Right,
the-
right, exactly.
Shankha, just to clarify, the phi of slide 14 and the phi of slide 13 are different phis in general, right?
No, they are like, yes, in principle they can be, because the new fields, so okay, there's a catch here. So we might need to renormalize these wave functions, and then these phis could be different. So, and we could write these in different bases, which I'm coming to in one of the next few slides. We can write phi as some phi prime, but we have the choice of retaining those original phis or dealing with some new phis, which might simplify my
At
calculations.
the end of the day, these are partition functions, so the role of phis are some variables doing integral calculus.
Absolutely, and this phi is just a placeholder. It is multiple fields. It's integrated over multiple fields. So now, before going to this discussion that we were having about like the integrating out, I would like to point
But I
out
think
about
the spirit of this comment that you tried to make is that at low energy, the observables that we are looking at in the experiments, the relation of that phi can be very subtle when we write a UV theory.
Absolutely.
The phi present in the UV theory doesn't have to
Absolutely.
be exactly the same thing.
absolutely.
Yeah.
Yeah.
That's the
Yeah. So, sorry, this box is a bit messed up. So, before going into the integrating out part, I would like to impress upon you some local versus non-local operators. So, what are local operators? So, local operators are usually, we can describe them as polynomials in the fields of these operators or their derivatives or a mix of both. So, these interactions, they occur at a single point in space-time. So, that is why it is local. So, an example of it is phi squared, D'Alembertian phi squared. So, this is one example of it. Another is a non-local operator which involves non-polynomial functions of derivatives. So, we can have a phi squared and inverse, like a propagator, box plus m squared inverse of phi squared. So, these interactions are actually smeared over space-time. So, they are not local anymore. So, how do we deal with these kinds of operators? So, and how do these operators actually come into existence? So, these operators, usually these non-local operators, come into existence when we integrate out some heavy degrees of freedom, and these operators actually capture the propagation effects at low energies. So, what we can do is that, so now so this is like related to your question. So, this LEFT phi is not equal to LUV phi of H equals 0. What we need to do is that, so unless phi and H are completely decoupled, which is almost never the case, then the difference LEFT phi minus LUV phi comma 0 is something which is non-trivial and accounts for the effects of the heavy field exchange between the light fields. Yeah. So now if we have
Yeah, I mean, I don't understand that. So you said that the non-local operator will come from a propagation of a heavy particle.
Yeah.
But if the heavy particle is heavy enough in the first place, it should not be, it should be almost stationary, should not be propagating, right? If I'm taking it very heavy.
no, like why will it be stationary? This particle will still decay into other particles. It's not a
Okay.
fundamental elementary particle. It could be an elementary particle, but still it could decay into other particles. It's not a stable particle.
But if it were a stable particle.
If it were a stable particle, then we are not talking. So it could be a very heavy particle and it could be a very long-lived particle. Then the effective field theory would look very different.
Okay.
That's not what we are talking about at this moment.
Is this a property characteristics of this top-down approach?
Yes. So now what we can do is that if the mass or the scale of this new physics is much higher than the energy in which we are dealing with, such an operator, such a non-local operator or the part of it can actually be expanded. So we can take m square out 1 by m squared out and we can expand it by binomial expansion, and we can get 1 by m squared minus box by m4 plus 1 and so on and so forth. So we will see that this non-local operator can be written down as a series of various contact local operators. So we can still deal with this non-local operator, but it will be a series, an infinite sum of local operators. You have a question?
Question in the sense, is it easy to figure out whether such thing is really appearing or not observationally?
So it is observationally, as I said, if you remember this colorful graph that I showed, that we will be able to discern such deviations through some very precise measurements, like either in some angular distribution or some differences in some tails and so on. So these are the indirect effects that through which we will be able to say that, okay, something like this exists, or something like the effects of operators. We do not yet have enough data to discern between various operators, and that is something that the community is working towards with our experimental colleagues. We are working with the effective field theory working group. So if you are even interested, you can give us a follow and you will know more about it. So some motivations for using EFTs. So simplicity, for instance. So why simplicity? EFTs actually reduce the complexity of the full theory, because we do not know what this full theory is. The full theory can contain many different kinds of terms. So it reduces the complexity of full theory to a finite set of effective parameters which captures the essential low energy dynamics. That said, there could be actually many operators. Like for instance, to give you a heads up, if we assume that there is no lepton number violation or no baryon number violation, then at dimension 6 there could be about 59 operators. So that's a huge number of operators. Huh? Standard model effective field theory at dimension 6. Calculability, this I'll be discussing in the next class. If we are dealing with some loop calculations, multi-loop computations, resummations over large logarithms, if we are dealing with EFTs, the calculations often become simpler, as we'll be able to see for SCET, for instance, soft collinear effective theory. So if we take effective theories, these kinds of calculations become easier. And just giving a broad overview now, I'll try to make some of these more concrete in the next few lectures. Model independence, again this model independence is a very strong word. It's not really model independent, but rather model agnostic, to be precise. So when the underlying UV theory is unknown or very complicated, the EFTs actually will allow us a systematic way in which the low energy phenomena can be understood. And also practical application, as I said, for like experiments like LHC, which run at around a few TeV, 1, 2, or like at most a few TeV. This requires an effective theory, so the high energy scale could be at much higher values, like 13 TeV or like at 10 TeV or even higher. And we are dealing with a TeV scale, so we can actually have an effective theory and simplify our calculations greatly.
True model independent effect EFT must be equivalent to bottom up.
So exactly, so bottom up, where everything is independent of each other, all couplings are independent of each other. That's a truly like model independent scenario. But once we try, as I said before, if we try to say that, okay, let's say that, okay, my theory is weakly coupled. So we all have our biases. So then we will be able to say something about the lambda, which is the high energy, the heavy scale. If we say that, say our physics is strongly coupled, then the lambda would change. But the ratio between the C over lambda to the power n would remain the same. So only the C and the lambda, they would change. That is what experimentalists would be able to constrain, this ratio from the bottom up approach. But beyond that, they won't be able to do anything. That's a theorist's prerogative, what they do with that. I'll be discussing like with some illustrations in the next or the last talk, the last lecture, how we can map on the same graph the bottom up approach and the top-down approaches. So to give you a heads up, like because you are curious, say I have multiple operators. Is there supposed to be a light going on here? Say I am trying to understand these two operator coefficients C1 versus C2. Then from all the data that I have and from the bottom up approach, I get this contour. So this is from the bottom up approach where all the operators are independent of each other. Then say I take model number 1, and from the theoretical understanding I get this region. This is say from model 1, and from model 2 I get say this region, and then everyone can put their favorite model on top of this graph. So what happens is that this M1 and M2 region, these do not change because these are from the theory. So a theory integrated out, C1 is a function of the model 1 parameters or the model 2 parameters. C2 is a function of either the model 1 or the model 2 parameters. However, this region is a model independent region. With more and more data, what happens is that this region would become more and more precise. So what could happen is this could shrink. So it could happen that it becomes like this, or if some new results here.
It is because it could be, that intermediate regions also, there could be some models that we don't know.
Exactly. So
because models are, cooked up by us.
Exactly.
And it's not coming from any theory.
Exactly.
Any observations.
Absolutely.
So the entire space can be filled with, tens of models actually.
Many models.
So it's just that we are not.
Yes. So I'm coming to that. So this is under the assumption that we have not found anything between the electroweak scale and this cutoff scale. We have not found any new physics in this spectrum. If tomorrow, hypothetically, we find something either here or in the flavor sector, what we would only do is we would change the definition of the standard model. So the standard model will include some new field like an SM prime, if I say, and then the SMEFT. So this is the electroweak scale, this is the UV scale, the new physics scale, and this is say the that is the 8th scale or whatever you say. And then I am saying that the assumption here is that in this graph is that we have not found any new physics in this region. And that is why we are basically what we are doing is that this entire region will keep on shrinking with more and more data. What might happen is that after collecting a lot of data, this model M1 starts to become disfavored, or many such models start becoming disfavored. Some models will start becoming more and more favored. And then we see all these pairs of graphs, C1 versus C2, C1 versus C3, and all possible combinations. We see it's a tedious job. It could be done with a machine learning algorithm. And what we do then is that we will be able to say what classes of models are actually good models. Right now, we take model after model after model. Experimentalists do not have that much amount of person power, and what they do is that, okay, like we are studying one model after another with no guarantee what's going to happen, because every model comes with a lot of baggage. Until we find that baggage for that model, we are never able to say, okay, this is the model that's true. So if tomorrow, say for instance, a particle is discovered, it could come from many such models. So that particle's sole discovery is not our final answer to what model we are going to have as our bigger theory.
So, Shankha,
Yeah.
Ideally, let's say in the limit of infinitely precise experiment, there will be a point on the C1, C2 plane.
Yes.
Right. So let's say we don't have the experimental results, but you have a family of models.
Yeah.
And now you're doing better and better calculation, and you see a subset of this family
Yeah.
starting converging on this plane.
Exactly.
Is that a right way to look forward to see like which models are probably the right models describing nature, and which point in the C1, C2 plane can be favored by nature just by looking at the convergence of this model contours.
Not just C1, C2, but all CICJs,
all Cs in the high
and all these
dimensional.
models. So that would give us finally CICJ, I running from 1 to say 59, J running from 1 to 59, I not equals J, and then we have all of these models. And finally, only a handful of model type will be allowed.
So this
by the data.
consistency check can already give you like which models to throw away.
Exactly. So that's basically that's
having any data.
So that is one. So just to advertise a bit. So that is like the area in the LHCFT working group that I am heading. So we are talking between experimentalists and theorists. Experimentalists are providing us with these C1, C2 model independent plots. What we are making possible is for theorists all over the world to hand us over these M1, M2, Mn contours, and we will be plotting them on top of these and reviewing these after every few months to see with the new data which of these models. So this is an iterative process. This will go on for years, and then finally we will be able to say, okay, this class of model is disfavored, this is more favored. Yes.
Models without having to get any data.
So ideally, we just favor one point in this sequence.
Sure.
Now let's say you're not given, you don't have the experimental contour, but you just keep on improving different models M1, M2, M3. All of them under improvement should converge towards that point, which is nature. Yeah, yeah. So can you just check that some models are not converging towards a point, whereas a subset of model.
These blobs become
The shrinking of the contours. Yeah.
The M blobs remain the same. The M blobs.
So I'm asking that can you improve the theory?
The M blobs can only change if we have better theoretical predictions for these models. So if we have better theory uncertainty understanding, the thing is that right now the machinery is not there. Like there are very few people working on such high level of QCD and electroweak corrections, and they are mostly focused on standard model. How much time will they invest on like doing these? But it's very important that people do it, because as I always say that some physicists think that first we should discover new physics and then worry about
of course
higher order corrections. But I must mention that if we had that mentality, we would not have discovered the Higgs boson, because the Higgs boson's leading order cross section is a factor of 3 or 3.5 smaller than the cross section that we have now. Like Ravi is one of the leading authors who has calculated such corrections, and had these kinds of calculations not been done, we would have not been able to map the data with the Higgs cross section. And that holds true for any kind of BSM, but also it's not feasible. So like how much corrections for how many models can we actually do?
No, my question was not that sociological. My question was, let's say in an ideal world, people can do better and better theory in
this is why I'm not following that remark.
Okay,
improving a theory requires experiments.
No,
there is no theoretical constant.
Parthoda, improving the theory means that these regions are under some theoretical uncertainty assumptions. Like we have some theoretical uncertainty that we have understood. Say the calculations are done at leading order or next to leading order for this theory, for model number 1. What if we do these calculations at next to leading order plus next to leading logarithm? Then these regions actually can change.
Same theory, but
better understanding. Exactly.
And then these contours will shrink towards one point in this C1, C2 plane. So can you just study that convergence and try to see which are the possible theories which are suitable candidates, whereas which are the ones which are diverging away from a point and they cannot represent reality.
This is a good point. This definitely we can include in our discussions.
Just to understand what he's saying, so you're basically saying that if there are theories where you do better and better calculations and these things start shrinking,
it's shrinking, but the center on which they're shrinking is diverging away. in this C1, C2 plane.
Then you throw it away, right?
Throw it away.
You
That-
throw it.
yeah,
That's what
that's
you're
the
saying.
point. Yeah.
Without having data.
Without having data.
Shouldn't that happen for every theory? Because every theory
Yeah,
gets
so
a
that's-
perturbative
that's-
expansion.
Yeah.
And after
Yeah.
perturbative
Yeah, yeah,
expansion,
yeah.
you
So,
calculate enough,
so
it goes away.
whatever are correct theories, they should fall towards one point, whereas whichever are incorrect theories, they should go away, like fluctuate away. Yeah, so that can be a data independent way to check which are valid theories.
Yeah.
Yeah, you're basically suggesting that do a lot of calculations before putting a name here.
I'm not suggesting anything.
I mean,
Like-
that's the approach.
In principle,
Yeah.
in principle.
So I have a question.
Sure.
So let me just, if I may call this scenario UV completion within MH. It is
Okay,
like
yeah.
You have a local theory
Yeah.
at MH from
Yeah.
where you are integrating out and
Yeah.
getting it.
Yeah.
That is what these models are referring
Yeah.
to.
Yeah.
But that is not. My first question is that in such a scenario, non-local terms will be generic or not? Probably yes.
Probably yes. Yeah.
Okay.
Like the operator that I discussed above, like something like that.
Yes. Okay. If it is generic, then if there is an experimental observation that we can figure out whether such non-local terms must be working. or
So,
not.
like,
Then we can figure, because this is not the only way to
Yeah,
you
this-
know
this is not.
match results. There could be a bottom-up approach which
Absolutely.
does not have a UV completion within MH.
absolutely.
Right?
Yeah. Yeah.
There
Yeah.
is no connection to the higher order.
Absolutely, I'll discuss that. But the thing is that right now, to my knowledge, please correct me if I'm wrong, there is no experimental probe to see what kind of non-local operators we have. So, as I said, we expand these non-local operators as a series of local operators with a falling 1 over m to the power something. So, we can only test that. We can only test that, okay, these operators have been seen, and then build them to build this, like add them up to get this non-local operator. But directly observing this non-local operator, I have no idea. At least I have no clue. Exactly. Like all the frameworks that we have in the experiments, they're all.
I understand. Then why in the discussion this top-down approach is favored?
No,
What is the benefit
it's
of it?
not favored. It's basically a sociological question that, like, we want a UV model. That's basically what we want. Talk is going on later. Yeah. Thanks. Yeah. So that's basically what's happening. So it's a mostly a sociological question that we want a theory of everything. That's basically what's the driver.
This gives you the truly bottom-up approach will give you some ratios and all.
Yeah.
So that is that a limitation? I'm just trying to understand.
The bottom-up approach will only-
apart from sociology, is there any real benefit of having a model?
There's like I don't know, like from if it's a very personal question, right? A model builder would say yes. I would say that
That's a sociological. I'm
Yeah.
saying just separate yourself from the sociology and tell me if there is a real scientific benefit. Why would you like if there is a UV complete model under image?
if there's
Why
a
would you like that?
If
It's
there's a UV complete model, we'll be able to describe like whatever we observe through a fixed number of parameters, like the parameters of the theory, which
So reduction of the number of parameters.
Exactly,
That's the
they'll
only
be-
thing.
yeah.
Fine. Got it.
much simpler. Yeah. Yeah.
Rotates all kinds of.
Yeah, it comes with a price that there are many models that you can write.
Yeah. Okay,
That is the price.
I'm almost out of time for today, but like let's start like something called power counting. So I'll stop at this. So say for example I consider an effective action for a scalar field. So this is this SEFT phi. So I write it as the kinetic term, the mass term, a cubic term, a quartic term, and then a sum over terms, which is basically an effective term, which has phi to the power n minus 1 and d derivatives of phi. So there are basically, it's an n point function, there are d derivatives and there are n phi fields. So we have, in order to have this entire action to, okay, so one thing is that I'm again jumping ahead. So when we write the integrand for so e to the power is, so we basically take h bar is equal to 1, right? But if we reinstate the h bar, the S, the action, should have the unit of h bar. So that will actually fix the dimensionality of these various coefficients. Now what I wanted to say is that let's consider this x prime to be a fixed quantity, so it's a length scale. Now I do this transformation, x mu goes to xi of x prime. So what is the meaning of xi? So when I take xi tending to 0 for a fixed x prime, this means that we are going towards a very small x, like a very small distance, which corresponds to higher energies. On the other hand, if I take xi going to infinity, this would correspond to large values of x, which would correspond to lower energies. Now what I can do is I can do some transformations, so I can take x mu to xi of x prime mu, and I can see how this term looks. So I'll have for d4x, I'll have a xi to the power 4. From this del mu phi, I'll have 1 over xi squared. So this will be a xi squared. Every other term will be xi to the power 4, and finally this term will be xi to the power 4 minus d, because there were d derivatives. Now this canonical normalization we want for the kinetic term. So in order to have this canonical normalization of the kinetic term, we rescale the field again as phi goes to phi prime xi inverse. And then we write down the effective action once more. So the canonical term remains the same, the mass term remains the same. We see that there is a difference, there's an inclusion of the factor of xi in the cubic term. Then we see that there's no change in the quadratic term, and we see that there's some change in this effective term. So instead of lambda to the power n plus d minus 4, we have a xi lambda to the power n plus d minus 4. It would become clearer in the next class why I am doing this. So let me just quickly go ahead. So now they will produce the same S matrix element, yeah. So I have not done anything else. So now, as I said, that e to the power is is my integrand, e to the power is, and it's actually e to the power is by h hat, which we in particle physics we take h hat equal to h bar equals 1. So if we reinstate that, we will be able to, so this s should also have the dimension h bar. So using that, what we find is that, yeah, sorry, I jumped a bit ahead of, so I am coming to this h bar. So now what we see is that this d, if I define this canonical dimension, d is equal to n plus d minus 4, and remember when xi goes to 0, we are dealing with high energies or short distances. When xi goes to infinity, we are going to large distances or low energies. So when we have this d equal to n plus d minus 4, let's take this term, this m squared phi squared. We have this phi squared term, we have n equals to d equals 0, which is number of derivatives equal to 0, n is equal to the number of fields, d is equal to the number of derivatives minus 4. So we have d is equal to minus 2. Similarly for phi cube, we have d equals minus 1. So what we can say is that when d is less than 0, we have, when this xi becomes large, this term becomes relevant, this term becomes big. When we have phi to the power 4, there we have n equals 4, d equals 0, minus 4, so d equals 0, so it's a marginal case. So it doesn't increase or decrease. Lastly, this irrelevant is a strong word because these operators are going to be important. If we have d greater than 0, these coefficients are suppressed at low energies. So for example, an operator with n equals to 3, d equals 2 has capital D equals 1. So I'll end with this slide, the h bar counting. So to derive a general selection rule or counting, we temporarily reinsert the Planck's constant h slash. So the action S must have the dimension h bar h slash to the power 1, since the path integrand is e to the power I s by h slash. So by convention, the kinetic terms are not multiplied by any h bar factors, right? So each field with a quadratic kinetic term has a dimension h slash to the power half. It's needed in order to have this to be to dimension h. So then by using this, so thus an interaction with n fields has a coefficient with dimension h slash to the power 1 minus n by 2. So for these n fields, each field having 1 by 2, so n by 2, h 1 minus n by 2. So so if we go back into the term, this m squared term will have a dimension of h slash to the power 0. This kappa will have h slash to the power minus half. This lambda will have h slash to the power minus 1. And the c and d will have h slash to the power 1 minus n by 2. So these are the dimension countings. And
Understand that h bar is playing a role of just scale invariance of the partition function. Just
yes, it's basically power counting, like segregating the operators into like either we can segregate them in terms of the mass dimensions or in terms of h slash.
Yeah, I mean, instead of h bar, you could have just used any other parameter. And
yes, yeah. But because my integrand comes with the s by h slash, it's the most convenient one. So I don't think I don't have any time today. So I would have loved to talk about the Fermi theory, which is the first example of an EFT. But let's do it the next day, or can I take 5 minutes, Shantanda? I can't. Okay, I'll take the.
There are any questions, quick questions left? Yeah.
This discussion about the UV models
Yes.
in the C1, C2 plane.
Yes.
Like if it is a UV complete model, then it must have some unknown parameters, right? Then my question is, how are you constructing this contour in the C1, C2 plane without having an idea about those unknown parameters?
It's not a numerical. So it's basically so C1. Oh, that's a very good question. So C1 and C2. So this is a C1. It's a function of C1 and C2. I'm not assigning any value here. So it's a function of C1 and C2. So you can plot a 2D graph as a function of C1 and C2. It's a region. The value is not yet assigned.
But I think that the C1 and C2 themselves should depend on the unknown UV model parameters.
Absolutely, absolutely. So C1 is a function, Ci is a function, is Fi of all the parameters like say alpha 1, alpha 2, m1, m2 and everything that goes on in the model. So C1 is a function of that, C2 is a function of that. So C1 may not be a linear function of these, it could be a complicated function.